Hello friends, welcome to our Hariharan Express channel. Today another topic I will discuss regarding on cache memory with different mapping. That means how cache memory design different mapping when we will consider any kind of data from cache memory for any operations. So first of all we will see that what is cache memory and how different data is stored in cache memory and how data transfer from cache memory to CPU for any kind of operation. Okay. Now we see normally what happens, cache memory contains a number of data. What is the how much data can be stored in cache memory and what is the use of cache memory? Actually cache memory is a small memory for fast accessing data. Okay, for fast accessing data point of view we use the cache memory because it is small memory size. Whenever we will search any data in cache memory, we can immediately find out that data if available in cache memory, any data available in cache memory. If we go through any secondary memory or any other memory, it will take some more time to search the data is available or not. Okay, so cache memory is a fast small memory for accessing any data at any time. If the data is available, we can get data very fast from cache memory. For that reason, it is very near to, it is established very near to CPU and main memory. In between CPU and main memory, cache memory is there. Okay, I will show you what is the concept of where it will be placed. And if the active portions of the program and data are placed in a fast small memory, the average memory access time can be reduced, because whenever we operate any kind of operation for any data, then we have to search it, the data is available, where is available. If we go through secondary memory or any other memory, then it will take some time. If we cache memory, immediately we can access the data if data are available in cache memory. Okay, so the average memory access time will be reduced if data is available in a cache memory. So reducing time point of view, we will use that cache memory. Another concept is obviously the execution time also reduce. So it reduces reducing the total execution time of the program whenever a program need to execute, and which is depend on the data which are available in cache memory. So that memory, particularly what we will discuss in cache memory, that is a very fast small access memory which is referred to as a cache memory. So cache memory is a very fast small access small memory. And if you analysis reduce or analysis point of view for cache memory, it is frequently used because since it is a very fast access time available or use fast access time point of view, we will use data in cache memory. So frequently you will search our data in cache memory. Okay, so performance point of view also it is very fast. The performance of a cache memory is frequently measured in terms of quantity, which is called heat ratio. That means we will measure some performance whenever we access some data from cache memory. We use one technique, that is heat ratio. Heat ratio means that means whenever data need to access from cache, if it is available, if it is data available and access from cache, then we call as a heat. Okay, and another case is when the CPU refers memory and finds word in cache, it is said to produce a heat. That means data is available in cache. Okay. If data is not available, that doesn't mean that always data is available in cache memory. Sometimes data is not available. In that another case is there. So if data is not found in cache, then it is in main memory and it counts as a miss. Okay. That means if a data found in cache, we call as a hit. If not found in cache, we call as a miss. That means data is available in memory, main memory. So what is miss and what is hit, we already know through this kind of a concept. That means data available in cache we call as a hit, data not available in cache we call as a miss. Based on that, we have to assess or we have to search our words or data from either cache or main memory, cache memory or main memory, based on that. Okay. If it is accessed in cache, so obviously the execution time will be reduced. So it reduces the execution time for the program. Okay. So this is the basic concept of cache memory whenever we will search any data in cache memory. And another is the ratio of the number of, so how to define the heat ratio. Okay, I will explain very easy way how to design or how to measurement, how to measure the heat ratio where data is available in a cache memory or any other. Okay, the ratio of the number of hits ratio defines the number of hits divided by the total CPU reference to memory, that is hits plus misses. Okay, is the heat ratio. That means heat ratio is defined in another way, like I will show you how to design the heat ratio. Means heat ratio design number of heat by, where heat, the heat means number of data when accessed from cache memory. So we find out the number of data, we can tell as a heat, number of heat. Okay, by another is a CPU reference to memory. Okay, the CPU reference in memory, okay, CPU reference in memory. That means here number of heat by, whenever CPU reference means two kind of things we go through CPU. One is number of heat plus number of miss. Okay, CPU reference is both number of heat plus number of miss, then combination of that we call as a CPU reference. So heat ratio, we can write heat ratio is defined as a number of heat by number of heat plus number of miss. Okay. Similarly, we also calculate, that is a miss ratio. We can calculate miss ratio. Same, very simple way. Number of misses, okay, or miss by similarly number of heat plus number of miss. Okay, number of miss we can calculate in this way. So miss ratio, heat ratio, miss ratio. That means heat ratio defined as number of heat means number of data available in a cache memory. Okay, then we call this one. Similarly, miss ratio, number of data available in a main memory, not in cache memory. Okay, That means number of miss means number of data not found in cache memory. That means number of data not found in cache memory. Then miss ratio also find out. Okay. So total reference means we can write total CPU reference. CPU reference means number of hit plus number of miss. Okay, number of hit plus number of miss, then total CPU reference. Whenever a CPU want to do some work, then it will refer to reference the data. If data is found in what cache, suppose found in cache, it is found in cache. Okay, it is not found in cache, we can not found in cache. Okay, this is the basic concept regarding on this. What is the number of hit and number of miss? In this way we have to calculate. Okay. Now we see how this is defined other part. So hit ratio is best measured experimentally by running representative programs in the computer and measuring number of hits and misses during interval of time. Particular time, how many number of data accessed from particular cache and not accessed from cache, that will be determined by this ratio or that hit ratio or miss ratio. Okay, that means we can find out immediately, that is number of data is available in cache or not. The basic characteristics of cache, it's a fast access type, because cache memory used for fast access time. That point of view we use the cache memory. Okay, the designer design a cache memory in such a way that it used for fast access type, fast access of data from cache. Therefore, very little or no time must be wasted. If you use cache memory, no time wasted when searching for words in the cache. Okay, very simple or important characteristics of cache. There is no time wasted when searching for words in the cache. Okay, so this is the basic concept regarding on cache. For searching point of view or accessing of data in cache, we will use this cache memory like this. Okay. Okay. So now we see that a data transfer of or transfer of data from main memory to cache memory is referred to as a mapping process. That means whenever data we access or transfer the data transfer from main memory to cache memory, then we go through some mapping process where which data need to access. So mapping process is there where data can be transferred from main memory to cache memory. So whenever I go through mapping process, so some category of a mapping process are there. So normally three category or three types of mapping procedures are there, which is practical interest when considering the organization of a cache memory. That means whenever we store some data or access some data from cache memory, some mapping procedure is there. So we consider three category of a mapping procedure. Okay, what are those? Those mapping are, that is associative mapping, direct mapping and set associative mapping. Three mapping are there in cache memory. We go through that three type of mapping and how the data will access through this mapping we will discuss one after one. Okay. Now we see again the main memory. Suppose we will consider some that is memory size in a main memory and as well as a cache memory. Based on that we have to access some data, not all data or size of data. We will discuss that part. You see the main memory, let consider the main memory, suppose 32 words of 12 bit each means each word contains 12 bits. Okay, 32 k words, that is main memory capacity we will consider. And another is similarly cache memory capable of storing 512 words, okay, and words at a given time. That means main memory contains 32 k words, each words having 12 bits, and cache memory having 512 words. And every word stored in cache, there is a duplicate copy in a main memory. Whenever stored in a cache, there is a duplicate copy in a main memory. Okay, every word, suppose any word stored in a cache. And a CPU communicates with both memory. Whenever CPU want to do some work through words, they communicate both memory. And first sends 15 bits to the cache. CPU, what happens, it sends first 15 bit address to cache. And if there is heat, that means if data is available in cache, okay, meaning this, because if there is heat, means data is available in cache, then what happens, CPU accept 12 bit data from cache. Okay, CPU access 12 bit from cache, but it sends 15 bits address to cache, but it access 12 bits from cache because 12 bits data is there in cache. Okay, if there is a miss, so obviously we cannot find out. Okay, if there is a miss, then CPU reads data from main memory. If not available, I told initially, if data not available, it is available in a main memory, and the word is then transferred to cache. Once data is not available in main cache, then it will search in main memory or reads from main memory, then transfer to cache. After that, it will use the data from cache. So very simple way, CPU sends 15 bits address to cache for any data. If it found, then what happens, 12 bits data it will collect. Okay, and if not found, then it reads from main memory and transfer the data or words to the cache memory. Okay, this is the basic concept. Next you see, I will show you how that is different data is recognized, okay, or through memory. Okay, now I will show you the position of different memory with a CPU. Very simple way, that is mentioned here. Here you see CPU is here, okay, cache memory is here, then main memory is here. Whenever it needed any data or words from memory, CPU use first cache memory here, very near to here. CPU access data from cache memory. Okay. Then what happens? If it found, then it is used. We can call as a hit. If not found, then that is a search in a main memory and data transfer to cache memory. Okay, like this we can consider this kind of structure in cache memory. Basic concept is there. Always CPU use the cache memory for any kind of operation. Okay, and now we have already discussed there is three category of mapping, that is associative mapping, direct mapping, and a set associative mapping. These three associative mapping we will discuss. Okay, now we go through this first one, that is associative mapping. Associative mapping is the fastest and most flexible cache organization uses in associative memory, and it is the memory which is fastest and most flexible cache organization uses in associative memory. Okay, and this memory actually stores both address and content of data. Okay, that means associative memory whenever store any data, it store both address as well as its corresponding content of data of the corresponding memory word. Suppose any memory we have to store both address of memory or address of word and data of word. Okay, that it will store. And this permits any location in cache memory, cache to store any word from main memory. Okay, so this particularly whenever we store any data or a word, then it identify a particular any location in cache memory, okay, from main memory. Suppose you need to locate or store some data, okay, and I will show you that is what is the format of that associative memory, and through certain diagram I will show you. Okay, and the address, whenever go through some address, I told that whenever CPU refers some data from cache memory, it is stored in 15 bits address. Okay, out of 15 bit address, what happens? 5 digit octal number used for address, and its corresponding 12 bit word I will show you, that is contain 4 digit octal number. I will show you that part. Okay, whenever you go through that, that is associative memory. Okay, so now you see other part also there, like you see very simple way. CPU store our data or that is store the word in a different ways. Initially what happens, CPU maintain the address for any data or words through 15 bits. You see this 15 bits, okay, 15 bits data store in a cache, and that is whenever our data need to search, then initially that data assigned to argument register. This we have already discussed, that is argument register. Okay, this argument register it will first assign, and through this argument register it is that is defined, and also it is compared with this associated memory. We have already discussed that how argument register data compare with associated memory, then it will retrieve the data if that is data is available. Okay, here contents, you see very simple way, here that is 3 words we will consider: word 1, word 2, word 3. 3 word we just maintain, and each word contains some, one is address part, another is data part. Okay, very simple way. Word contains this address part, another is data part. In this way each word is maintained, and it contains 15 bit. Okay, both combine of that. Please see that this whenever we search our data through argument register, they will search this argument register. We just put what we need to search, they will search through argument register. It will assign some data as our requirement. That data search in either through word 1, word 2 or word 3. That means the argument register contains our data, that argument register data search in different words with both address. If your address is the same, automatically that data can be retrieved. Suppose this data, this address same, for example, what are the data we assign in argument register, that data, okay, that address with the corresponding data can be retrieved. This data can be retrieved from this associated memory. Okay, like this we have to design this associated memory or associated mapping in cache memory. Now we see whenever define individual part. Now we see very simple way, same thing I will explain. CPU address of 15 bits. I will show that already mentioned, that is CPU address 15 bits. Okay, so CPU address 15 bits is placed in argument register and associative memory is searched for matching address. Because you see, whenever we CPU placed 15 bits data in its argument, it has also address of data. That address data search in a different words. Okay, that is the basic concept. If address is found, that means argument address data in argument register found in words. If address is found, the corresponding 12-bit data is read and sent to CPU. Okay, here you see 15-bit address stored in a argument. Okay, but if it is found, for example, it is found that address here or any. Okay, the corresponding 12-bit data, actually 12-bit data in cache, 12-bit data in cache. Okay, 15-bit data, 15-bit address matching through argument register with the word 1, word 2, word 3. The corresponding 12-bit data will be retrieved from cache. This is the cache, associated memory in cache. 12-bit data it will be retrieved. But here is mentioned 4-bit data, doesn't matter, don't worry about this. It is 12-bit data can be retrieved if address is matching. Okay, so if address is found, the corresponding 12-bit data read and sent to CPU. If cache is full, for example, cache is full, an address data pair must be displaced to make room for pair that is needed and not presently in the cache. Suppose data not if there is a full, okay, cache memory is full, then make a room to store your data. Okay, whenever it is transferred from main memory to this cache memory. For the reason it is mentioned, if cache is full and address data pair, address data, whenever any word need to store, both pair address and corresponding data need to store. Okay, so address and data pair must be displaced to make a room for a pair that is needed and not present in the cache, because it is not available in cache, so it is needed to make one room in cache and store there. If match not occurs or no match occurs, if address is found, we can retrieve data from cache or associated memory. If not found, then what happens? The main memory is accessed for the word. Okay, main memory access the word, and the address data pair is then transferred to associated cache memory. Means if a data or a word not found in cache memory, then the corresponding data collect from main memory through both address and data pair and transfer to the cache memory. This cache memory again store. So data is not found here, then data collect from main memory and transfer to this cache memory with the transfer through this to this particular associated cache memory with the address and data. Some another data suppose not available, it is to it collect from main memory and transfer to this word, transfer to the cache memory or this associated memory as a new word with address and data. Like this, the different data can be searched or accessed through this associated memory. Okay, this is the basic concept of associated memory. Now another mapping I will discuss. Okay, that is here is associated memory. Another topic is like a direct mapping. Okay, I will discuss that is a direct mapping. Associated memories are expensive compared to random access memory. Suppose frequently you access data, so it is very expensive. Associated memory is very expensive because of the added logic associated with each cell. Because the last time I have already discussed that is associated memory, how it is designed. Okay, how it is designed, then different cell when create for associated memory, it is more expensive. Okay, for the reason what happens, it is a disadvantage if we randomly access memory, it will store the data, different data in a cell wise, and whenever you create cell, then logic circuits is required to create that cell where the data need to store. That is the disadvantage of associative memory. So for that reason, it is mentioned associative memory are expensive compared to random access memories because of added logic associated with each cell. Last class we will discuss, that is whenever number of cell will create, it is designed through certain logic circuit. So if more cell is required, so obviously it is more expensive. Okay. For the reason, what happens? CPU address of 15 bits is divided into two fields. To avoid that kind of problems, CPU what CPU is done? CPU address of 15 bits divided into two fields. One field is 9 least significant bits constitute index field, another 6 bits form a tag field. So total 16 bit address divided into two part. One part is a index field. You see, one part is the index field, another part is a tag field. So directly, if you go through associative memory, then what happens? So directly we will search as argument data to associative memory, but that is a disadvantage. For that reason, what happens? The CPU again divide that as 15 bits into two part. One is a index field, another is a tag field. Index field having 9 bit and a tag field having 6 bit. Okay. In this way, the address is defined. In the general case, there are 2k words in cache, 2k words in cache memory and 2n words in the main memory. Okay. In that case also, whenever define CPU address, that is they see that how many number of words in cache or how many number of words in memory. Based on that, they define. For the reason, suppose n bit memory address is divided into two field, then k bit for index field, k bits for index field, and n minus 1 key field for tag field. Okay. K field for cache, n field for main memory, but that is defined through that 15 bit address or n bit address as per this memory. Then k bit for index field and n minus k field for tag field. It is defined in this way. Okay. We will see that how it is defined or designed in a certain way. Then we will find out what is the reason behind of this. Okay. Okay. So here direct mapping cache organization uses n bit to access the main memory and k bit index to access cache. Okay. N bit address to access from the main memory and k bit index to access cache memory. So both main memory and cache memory both are used in a direct mapping. Okay. In this direct mapping both are used. N bit from cache memory, sorry, n bit address to access from main memory and k bit index to access cache memory. And here each word in cache consists of but the word and its corresponding associated tag. So whenever you define or design the word, what happens? That is in available in cache and consists of word and its corresponding tag. Whenever data store in associated memory or cache, store in cache, so both data word and associated tag we will consider for each word. And the tag field of the CPU address is compared with the tag in the word read in cache memory. Whenever we will compare, then what happens? Tag field of the CPU is compared with the tag field from cache. That we will compare. Once two tag, so that means you see very simple. CPU address contains tag field and compared with the tag field from cache. If both tag is matched, then what happens? There means hit. If both two tags means tag from CPU, tag from cache, both tags is matched, then what happens? There is a hit and the desired data word is in cache. That means that data is in a cache memory. Only not all data need to match. Only through tag. With two tag, is matched, so there must be a data in cache, then we call as a hit. So that is a hit and desired data were in cache. If there is no match, so that means tag is not matched, then there is a miss and required data read from main memory. Suppose the tag is not matched, that is what miss and required data collect from main memory. CPU required data collect from main memory. Okay, this is the basic concept. So it the important part of this direct mapping is a tag. Once a tag is defined, the every data that is matching or compared with a tag. Okay, that is the main part of this direct that is mapping. If we go through direct mapping, we go through in this way. Okay, so now I will show you how this direct mapping is defined. Very simple way. Here you see that is total. We have already discussed CPU contains 15 bits address. Contain 15 bits address defined by CPU. CPU defined 15 bits address for data which is available in main memory as well as cache. Okay, but it will search through other way. If we go through direct mapping, then what happens? That CPU 15 bit address divided into two part. One part is a index part, another part is a tag part. Okay, here index part, since it is 15 bit, you see 15 bit, suppose index part is a k bit, obviously 6 bit for tag, because 15 minus 9, there are 6 bit. Okay, so this is 9 bit, so 9 bit for index and 6 bit for tag. Total sum of that data is a 15 bit address. Okay, previously we know that already, that is n bit address. Okay, n bit address, from n bit address, k bit for index. Okay, k bit for index and n minus k bit for tag. Obviously, okay, n bit address, suppose we will consider k bit for index. Here is a k bit, we can tell it is a k bit, it is a n minus k bit. Okay, it is a n minus k bit. So if it total is 15 bit, so 9 bit for index, n is 15, n minus k, so 15 minus 9, that is 6 bit for tag. Like this we have to design the total address by the CPU. So here you see that index, both that memory it is used. That is you see index is used for main memory, again that index also used for cache memory. You see I show this part particularly very simple way. Okay, so you see this particular index part, it is used for both main memory as well as cache memory. This is cache memory, this is main memory, and main memory design 32K into 12, this main memory, and address part, you see address part is 15 bit and the data part is 12 bit. Similarly, if we go through cache memory address part is 9 bit, data part is 12 bit. Why it is 9 bit? Because already mentioned index part. Here you see 9 bit is for index, this is used for cache. Okay, this is used for cache, this index is used for cache memory. So like this it is defined. Now we see tag is 6 bits. 6 bits is contain both main memory and also this cache memory also. I will show you next figure, then how it is defined, we can also understand that part. Okay, so now you see this tag, actually it is matched with a 6 bit tag. Once is found that 6 bit tag compared with the cache memory, then we call as a hit. If not found, then it is collected from main memory and transfer to cache memory. After that it will operate through this cache memory. Okay, so very simple way it is defined. So very simple way of this 15 bit address, one part is the index part, another part is the tag part. Index part is, suppose if you go through 15 bit, index part is 9 bit and tag bit is 6 bit. Okay, like this it is defined. Both index also they will design and this tag we just compare with the tag, no need to address that bit, index bit, only tag. Through tag we can find out, okay, that is available in a cache memory or not. Now we see here very simple way I will show you direct mapping cache organization, how it is designed, how it is defined, very simple way. Okay, you see, if we go through this one, direct mapping cache organization, one part is the memory address defined in this way. If it is main memory designed in this way. So main memory, what happens? Main memory, one part is the address part, another part is the memory part. Here is a memory address, it is address part, okay, and this is a data, memory data, okay, it is mentioned already, it is a memory data. This memory data is defined in this way, okay. So now we see how this particular direct mapping map with the cache memory. Very simple way I will show you, then you can understand. You see, if we go through memory address contains previously defined through CPU, and here you see very simple way I will show you. This memory address contains, here is a suppose 5 bit, here mentioned suppose 5 bit, we will consider suppose 5 bit. First 2 bit is tag, remaining that 3 bit per index, okay, combine of that to make that memory address. First 2 bit is tag, next 3 bit for index, so combination of that to make a memory address. But if we go through cache memory, it is defined differently, separately. Tag you see 0 0, here index also 0 0, just combination of tag and index to make a memory address. You see 0 0 0 0 here, okay, 0 0 0 0. Similarly, if you go through last part of this cache memory, you see tag is 02 and index is 777, here 02 777. First part is tag, here mentioned, another part is that is index. Similarly, combination of tag and index to make that memory address. Once this tag, you see this tag is comparison with the CPU, they find out the corresponding data. This data we can find out. Very simple way it is defined. Okay. So if we compare it with the cache memory and main memory, we can go through in this way. Very simple way it is defined. Okay, I hope all of you understand this kind of very simple concept. If we go through main memory, data memory is defined in this way, and memory address also defined, combination of both tag and index. But if we go through cache memory, it is separately it is defined, because CPU identify to search or identify tag for searching the corresponding data is available in a cache memory or not. So it is separately it is defined. If we go through main memory, the combined of that memory address is defined in this way. Okay. So very simple way it is designed for that is a data address, okay, through tag and index address in this way. Very simple way it is defined. Okay. Now see all of you very simple design of that main memory and cache memory. Okay. Okay. So now another remaining part also I will explain how it is defined. Okay. Now see, here is another way we can define. Okay. So you see, continue that direct mapping. It is whenever a storing point of view or any previous data or anything through tag, we will see that what is the concept behind of this. So it is then stored in the cache together with a new tag. Suppose we store some data, so through new tag we have to store and replace the previous value. What is the previous value there? We have to replace. Okay. So the disadvantage of this direct mapping is that heat ratio can drop. Okay, heat ratio can drop the disadvantage like this, direct mapping is that heat ratio can drop considerable if two or more words of those address have the same index but different tags. Okay, same index is there because we have already discussed here. You see, we can also consider same index. Here you see very simple way. Index is the same here. Here index same, here index same, here index same, here index same. Same index you see, same index, here is same index. But tag is different. Same index tag is different. Then what happens? You see, in that case some problem will arise. For the reason that the disadvantage of direct map is that the heat ratio can drop considerable, heat ratio, because number of data is there, heat ratio can drop if two more words address have the same index. If same index, how to find out the actually that particular data need to use or access. So there is some problem. So for the reason that will be the heat ratio can drop and different tags are accessed repeatedly. Suppose number of tags accessed repeatedly. Okay. So that is the one kind of disadvantage. Another is the direct mapping example just describes a block size. So to avoid those kind of things, direct mapping just example just a block size of one word. And index field is now, the index field previously in single, now index field is now divided into two part. One is block field, another is a word field. Okay, index field is a two part, one is a block field, another is a word field. Now we see how it is defined for this. Okay, now we will see very simple way we design that part. How the index bit that is a word part, previously what happens, index and tag part we have already taken. After that the data is stored. Here you see index part is defined 0000027, tag field 01011. So data is there. Like this we have already discussed that part. But here is you see, if index is the same, so tag is same tag, number of index are there. So same tag contains one kind of a block. Okay, same tag having one kind of blocks. What are the index? Index is different. You see different index. Same tag, different index. So same tag contains one block. Similarly here 0, 1, 0, 2, like this. Suppose the number of tags are there. Then one block we will consider. So it is designed how many blocks depend on the capacity of that address. Okay, based on that we have to design number of blocks. So now we see tag is one part, another part is block and word. Block and word is index. Okay, index defined block and word. Here is block and word to make that index. Very simple way it is mentioned. One part is tag, another part is block and index to make that. Index is word part actually, to make that index. In this way, here we have already see that is a tag part is already 6 part, but now index part is defined block and word. So block part is 6 bit and word part is 3 bit. Okay, so total is a 9 bit. 9 bit is divided into two ways. One is a block part, another is a word part. In this way. Okay, so based on that we have to define how much bit is required for index. So now you see another part, that we see that another part how it is defined. In a 512 word cache, we have already discussed 512, we consider 512 word cache. There are 64 blocks. Suppose 512 words in cache we will consider. So how many blocks, how many tags we will define in this way. 512 words we will consider 64 blocks and each block contains 8 words. So very simple, 5 here 512 is equal to 64 into 8. Okay, that means 64 is block, 64 block, each block 60 block of words. Okay, 64 word each block, 64 block and 8 words. So it contains like this. So 64 into 8 total words we can find out. Okay. So block number is specified with a 6 bit. Since it is 64. 64 means what? 64 is 2 to the power 6. So 6 bit is required. So block, whenever defined the block size, so it contains 6 bit because 64 block is required. So 6 bit field is required. Okay. And the word within this block is specified by 3 bit because 64 into 8 means what? 2 to the power 3. Okay. 3 bit is required for word. So very simple way. So 6 bit for that block. You have already mentioned block is how many? 6 bit. 6 bit means 64, and a word contains 3 bit. 3 bit means 8. Okay. 64 into 8. Total index size is 64 into 8. For the reason here you see very simple it is mentioned that block 1, block 2, block 3 up to 63 block. Okay. 63 block means a 6 bit. Since it is mentioned 6 bit means 63, 0 to 63. Total 64, 0 to 63. 0 to 63. Like this we have to define. Okay. So now you see another part is a tag field. The tag field store within the cache. Okay. And is common to 8 word in the same block. Okay. 8 word for same block because block contains the same tag. So tag field store within the cache common to 8 words within the same block. Why it is 8 words? Because you see if this tag contains what? This cat 0 1 suppose this contains same word. Here contains same word because 0 1 tag same word. So it contains same word. 8 words. Sorry, it contains all 8 words of the same block. Same block. You see, same block 8 words because 8 is there. Same word. Sorry, 8 word in the same block. Same tag 0 1. It contains same block with 8 words. It is defined in this way. Okay. And every time miss occurs, sometimes some miss also there. Every time a miss occurs, so in this case what happens? An entire block of 8 words must be transferred from main memory to cache memory. Suppose that word is not available, then what happens? Entire that block with 8 words must be transferred from that main memory to cache memory. Okay, this is the overall concept regarding on that direct mapping with the block, tag and index. Okay, in this way we can also define. Now we will discuss regarding on that is set associative mapping. Set associative mapping. The disadvantage of direct mapping is that two words with the same index in their address. Normally, what are the first of all we will discuss regarding on previous disadvantage, then we will define another set of mapping or one next mapping. Disadvantage of direct mapping is that two words with the same index in the address but with different tag values cannot reside in cache memory. Okay, two different tag values cannot be reside because that is another disadvantage. If it two different tag values, then same index different tag value, it is not right way. That is another disadvantage at the same time. Okay. For the reason what happens, we will improve that mapping through set associative mapping. Through set associative mapping it will improve. Okay. Now set associative mapping overtake or over that direct mapping organization. How? Each index address refers to data words. Each index address refers to data words and their associative tags. Okay. Because index address we have already discussed that in index address a block and another word. In this case what happens? So each index address refers to data words and their associated tags. A word with the associated tags. Okay, how it is defined? For example, we know that each tag requires 6 bits. We have already discussed. Each tag is 6 bits. and each data word has 12 bits. Data words have 12 bits. Then what happens? Because 12 bits it contains in a cache. Tag is 6 bits. Then what happens? The word length is defined 6 plus 12 bit. 6 per tag, 12 bit for that word, data word in a cache. 6 plus 12, total is 18. 18, that is a total word length is defined. And if we go through set associative mapping, that is 2 ways or 2 data words we will define at a time with tags. So here is a tag is 6 bit, you see 6 bit for tag and 12 bit for data word, 12 bit for data word. So 18 total data is required for word length. So if we go through 2 times, that because it is set associative, it is 2 times you define. So 2 into 6 plus 12, the 2 into 18, that is 36. You see 36 bits is defined or designed for set associative mapping to avoid that direct mapping. Because direct mapping, what happens, some problem is there, index that is some problem, and it's different tags with the same index create another problem in direct mapping. To avoid that part, what happens, we just consider set associative mapping where only bit, tag and word length is required. So directly we can also use in this way, but 2 times we have to design with the associated tags for set associative mapping. Okay, now we see how it is defined or designed that associative mapping. I will show you first defined theoretical, then I will show you. Now see, an index address of 9 bits. Index address of 9 bits we have already discussed, because one part is a block, another part is some word to make that 9 bit. Okay, or index part only 9 bits can accommodate with the 512 words, because 9 bits to the 9 is 512 words. The size of a cache memory is what? Initially it contains 512 words, and each word contain that 36. We have already discussed with the that index and tag. Okay, tag and data. So 512 into 36, because we have already discussed that is word length is 36 bit. So 512 into 36. So it can accommodate, obviously you see, it can accommodate 1024 words of main memory, since each word of cache contain 2 data words. Okay, so since it contains 2 data words, it is defined through 1024 words. Now we see how it is defined. In general, set associative cache of size k will accommodate k words of main memory in each word of a cache. What are the cache memory, cache data? They will accommodate with the k words in the main memory. If we set associative cache of set size is k, because here what happens, if you go through k main memory, the size consists of k is equal to, we know that k is equal to how much? K is equal to 1024. So in main memory it is defined with a k, maybe 20k, 30k, 40k, doesn't matter, with a k. So for that reason it is mentioned it can be accommodate 1024 words of main memory, since each word of cache contains 2 data words. But here what happens, set associative cache of size k will accommodate k words in main memory. So maybe 30k, 40k, something different, that is with k words we will use. And the words stored at address, suppose 01000 and 0200 in main memory are stored in cache memory in index address 00. So tag part is 01 or 02, but address part is 00 in cache memory. When main memory defined in this way, cache memory defined only with the index part. So these first 2 part, here is 2 part. One is here is a tag part, here is a index part. Okay, if you tag index in main memory defined, then index part is defined in a cache memory in this way. Very simple way it is mentioned. Okay. Now we see how it is defined. Very simple way. You see, two-way set associative mapping cache is defined in this way. Very simple way. One index. Previously what happens, both index and tag block is there, so very complexity is there. But we go through this particular part in a two-way set associative mapping is very convenient way. Now we see how it is designed. Here you see number of indexes is same index, not repeated. Index 0002 777. So no problem. Tag is defined 011 tag. Here is another tag. So data is there. So same index, different tag or data can be defined in this way. So it is very convenient to define that two-way set associative mapping cache. Okay. So there is no confusion because one part is there, index part is there, corresponding data we can get it. Here another tag is there, corresponding data is there. There is no problem. So index, tag and for particular data we can access in this way. Okay. So this is the another concept regarding on two-way set associative mapping. Okay. In this case, you see how it is defined and designed. This design is there. How it is analyzed? You see. Similarly, if we go through some words address 0277, another is 0077. It depends on that. Okay, I have already discussed that. Index is 77. You see, index is 777. Tag is 02. Here is 777. Tag is 000. Are stored in cache with address 777. So this particular index, this index stored in a cache. So directly go through that index, we can find out the corresponding that data. Okay, where is available in a cache. When a CPU generates a memory request, the index value of address is used to access the cache. So no need to use the tag. CPU generates a memory request and the index value of address is used to access the cache. Okay, and the tag field of CPU address is then compared with both tags in the cache to determine match occurs or not. So first of all, it will match with the index. Okay, you see, match with index. Which index will match? After that, compare with the tag. If index is matched, compare to tag either tag 1 or tag 2, whatever the tag is matched. Based on that, the corresponding data will be retrieved. Okay, because you see very simple way it is mentioned, like a first index, this index will match because index part is in a cache. If a cache index is the same, then corresponding data means a tag data it will match. So for that reason, here mentioned the tag field of the CPU address is then compare with the index in cache. CPU the tag field in the CPU, then compare both tags. Okay, in the cache to determine if it match or not. If it match, then corresponding data will be retrieved. Okay, corresponding data will be retrieved. In this way, the data can be retrieved from that cache memory. Okay, in this way, data matching with the cache memory. So I hope all of you understand how the different mappings we consider, either that is associative mapping or a direct mapping or a set associative mapping. Okay, so I hope all of you understand this particular cache memory with a different mapping. So this is very typically concept design that mapping. Normally we know that cache memory is very frequently used to access the data, but whenever searching our data in cache memory, we go through certain mapping. Okay, that mapping also designed in a different ways. Whenever necessary, we see that our data is there or not. If data is there, then we can access data from cache memory. We can call as a hit. If not there, that is you can call as a miss. So in this way, different mapping and hit and miss, hit ratio and miss ratio also we design through this cache memory. Okay, I hope all of you understand this topic. thanks to all to watch my videos, and please subscribe my channel, and if you want to give some comment, you can give comment, by which we will improve our videos and progress our channel. Okay, thanks to all.